Stanford University.
All right, so welcome to Lecture 8 of CS193G. Today, we're going to start our series of invited talks from some domain experts from NVIDIA. And today, Nathan Bell from NVIDIA Research will be talking about Thrust, which is a productivity library for CUDA. So Nathan has been with NVIDIA in research for about 2 years. He's been doing along with Thrust, a lot of research on sparse matrix vector operations on GPUs. Before that, he did his PhD at the University of Illinois. So please join me in welcoming Nathan.
Thank you, Jared. Okay, so today I'm going to talk about Thrust. This is a library I work on with Jared. And I'll start out with just an example, because I expect some of you will not be familiar with things like C++ or the STL. And this just gives you a sense of how to write a program with Thrust and what it's capable of. So this is a file. This is a complete Thrust program. You would save this to a .cu file and compile with NVCC as usual. And it should be clear what it does. It generates some random values on the host, and it stores it in this host vector container. Actually, can I get a show of hands? How many people here are familiar with the STL or have used it in the past? Okay, well, that'll make things a lot easier. So anyway, there are different algorithms and containers in Thrust. So there's a host vector container, a device vector container, and then we just tell it what type we want to store in those cases. And these are all analogs to the STL vector container. And in addition to that, we have algorithms like the generate algorithm. Just invokes a function, in this case rand, and stores the result in each element of the array. We can do host-to-device copies using just an equals operator. So this avoids the need to do CUDA malloc, CUDA memcopy, and so on. That all happens under the hood. And you can also do things like sorting very concisely. So in this case, we're generating some random values on the host, saving them in this host vector, transferring that to the device using this equals operator, sorting on the device, and then copying back from the device to the host using the copy algorithm. So if you're not familiar with C++, these things like thrust, : that's just a namespace. So this is the way we refer to things in Thrust. And the things in green are Thrust algorithms, like sort and copy, or generate, or Thrust containers, so device vector or host vector. So that's why we've highlighted them that way. Okay, so for the remainder of the talk, I'll go through sort of what the features and functionality in Thrust is, and sort of how that's implemented and things you can do with it. And later on, we'll get to sort of best practices with Thrust, so how to make your programs run as efficiently as possible. Okay, so the idea with Thrust is that we want to leverage CUDA, but we want to do it in a way that doesn't require that we do the low-level programming that we sometimes might need to do. If possible, we want to program at a high level and just say, leave it implicit how to perform that operation. Just say we want to reduce an array or sort an array. And we'll often just distill things down to parallel primitives. So if we can work out how to implement your algorithm in terms of things like stream compaction or sorting, those parallel primitives, then that should map nicely to the kinds of algorithms we have in Thrust. And you won't need to write your own CUDA kernels for those kind of operations. We also want to make sure that Thrust is high performance. So it's important that the algorithms we provide are carried through and achieve a large part of the peak performance that you can get with CUDA. And we also want to make sure it's interoperable with CUDA C and C++. So if you have an existing CUDA code and you've done your own malloc, CUDA malloc and CUDA mem copies and so on, then you can still add Thrust to that without too much effort, and vice versa. So if you have a Thrust container, a device vector, it's very easy to get out a pointer to that data and toss that into your CUDA kernel that you've written that does some specialized operation. Okay, so Thrust is a pretty close analog to the STL. So if you're familiar with that, a lot of these will look familiar. Sometimes we have to add a new version of the function because we don't have the same semantics. So instead of accumulate in the STL, we have reduce because we do this in parallel and we can't guarantee the same semantics that are provided by accumulate. We also have some other things like inclusive scan, things that are more important for a parallel library. But a lot of them are exactly the same. So sort is one-to-one analog of what you would get in the STL. And there are many other things like this. So I've just illustrated a few. In principle, we could have different containers. So if you're familiar with the STL, you have things like lists or maps, things like that. Currently, we only have vector, but in the future, we could add some more interesting data structures like that as well. Okay, so we'll look at a few features in isolation. Here I've illustrated what you can do with vectors, the host and device vector. So on the first line, we allocate a host vector with 2 elements, 2 integers. We can copy that from the host to the device just using the equals operation. So we don't have to tell it this is a host to device copy. It figures out where those 2 things live and performs the right copy automatically. And then we can also set elements, individual elements of the vector. So even though this vector lives on the device and requires, that we use the CUDA API to access that memory, we can do this sort of transparently. So when you do this kind of assignment and set the first element of the vector to a particular value, you get a CUDA mem copy, under the hood. So this is something you don't want to do too much because it implies a call to these API functions each time. So you don't want to set the elements of your device vector in a for loop. But if you just need to read back a value from an array or set a single value, this is a pretty convenient way to do that. Okay, if you have existing STL data structures, so in this case a list, you can very easily copy that data into a device vector. You just do the standard STL idiom. So if you're not familiar with the STL, I guess I should explain that this begin and end stuff, this is just a way of describing a sequence in either the STL or thrust. It just says begin at this point in the vector, or in this case list, proceed until you reach the end, and that defines a sequence. And in this case, we're saying to copy that sequence over to the device. There's also sort of a one-shot way of doing this using the device vector constructor. So anyway, this is just to illustrate that it handles a lot of the boilerplate code you might write if you just write using standard CUDA C. Okay, so the things returned by dvec begin and dvec end are in the C++ terminology, these are iterators. So you can think of them kind of like pointers, and basically a device vector iterator is a pointer, but it also tracks some additional information. It knows where it lives. It knows it lives on the device. And likewise, if it's a host vector iterator, thrust knows that it lives on the host. And the way that these specify sequence, as I mentioned before, the begin points to the beginning of the array, end points one past the end, and the way you can kind of think about it, and the reason we call these iterators, is that if you increment begin until it reaches end, you've passed over the sequence. And that makes sense whether it's a list, a map, a vector in this case, or anything. So we don't really leverage the other capabilities of iterators because we just have vectors, but it provides a nice interface to describe whether the memory is on the host or device. Okay, so you can treat iterators like pointers. You can take the difference of 2 iterators, and that tells you how long the sequence is. You can increment them, so if we want to change the sequence that we're describing from a sequence of length 4 to a sequence of length 3, we can just use pointer arithmetic to do that. So if you're familiar with pointers or iterators, then you can do all the same things with thrust as well. And here's another example. You can dereference iterators. So in this case, we're assigning to the first element of the array. We get this begin iterator at the beginning of the array, and we can assign to it. We can read from it. And we can treat it just like a pointer, ignoring the fact that it refers to some device memory. Okay. So you might say, why does this matter? A really nice feature of the iterators is not just that it manages the hosted device copies for us, or lets us poke and prod these arrays, but that it allows us to use the same algorithm in either case. So in this example, I have 100 or 1,000 random integers on the host. I copy them to the device, and then I could take the sum of them in either place, and I can just use the same algorithm. If you did this without iterators that knew where they lived, you'd have to have a reduce on device or a reduce on host algorithm that knew which algorithm to invoke. So under the hood, this is going to invoke a CUDA kernel. And this one, it'll just do a serial for loop on the host. And you get this sort of automatic dispatch for free. And this is the way all algorithms work. So if you do sort or anything like this, we have a CUDA implementation on one side and a standard C++ implementation on the other side. As I mentioned, if you want to if you have a container, so in this case a device vector, and you want to use that data in an existing CUDA kernel, say you just want to use thrust to manage your memory, not to use any of the algorithms, you can very easily get a pointer from that. So we have a device vector full of integers, and we just get an integer pointer to the beginning of that device vector using the raw pointer cast. So if you can write your entire program in thrust, then you won't need to do this. But generally, you'll have at least some things in your application that thrust doesn't handle perfectly, or just maybe not at the full speed that you want. And in that case, you can write a CUDA kernel to implement those operations. Okay. And you can do the opposite as well. So if you have some memory on the device that you've allocated with CUDA malloc, as in this example, in order to use that within thrust to make sure it knows which kind of algorithm, whether it's a host or device algorithm that it needs to call, you can wrap it up with this device pointer. So if you don't use device pointer and you just pass your pointer into this fill algorithm, thrust will assume that this is a host pointer, and that's sort of to conform with what the STL does. And it'll actually give you some, segmentation fault or something like that, because you're trying to dereference out a device iterator or a device pointer on the host. So anyway, you can go either direction. You can go from thrust to your standard CUDA C++ code, or vice versa. Okay, so as I mentioned, we use namespaces. So that if you're not familiar with C++, thrust algorithms will be prefixed by this thrust : STL algorithms will be prefixed by STD, and that's just to avoid collision. So we both provide sort functions, and the way to distinguish them is through these namespaces. And if you don't want to type thrust before each algorithm, you can use this using namespace at the beginning of your program. Okay, so to summarize what we've talked about so far, we've introduced containers. So we have host vector and device vector. These manage memory for us automatically. They handle the allocation, deallocation, and copying between the two spaces. We've talked about iterators. The iterators that we have are basically pointers, except they come with some metadata, so they know where they live. But if you really need to, then you can convert those back to normal pointers. And of course, namespaces. So all the features in thrust are available through the thrust namespace. So I'll go over this, I guess, pretty quickly, because it seems like most people are familiar with C++. The generic, in thrust, we have a generic algorithm. So instead of just saying you can call this function to take the sum of numbers of a particular kind, we just say, in general, we can either do like a generalized sum with no particular type. In this case, we can take the sum of integers or floats. Or you might want to do different operations. Instead of taking the sum of two integers or floats, you might want to take the maximum of them. So C++ templates are a way to incorporate that kind of generality into a library. So in this example, I have an add function, and I've left unspecified what type I'm going to add. And you can either explicitly say, when you want to finally use this add function, what type you want to use, either int or float here, or you can let C++ infer that information automatically. So if you saw before, I didn't have to tell it that I wanted to sort integers. I just said sort, and I gave it 2 iterators. That's the kind of technology under the hood that automatically infers what the type that needs to be sorted is, or in this case, what types we want to add together. Another way of doing the same kind of thing is through what's called a function object or functor. And this will look a little weird if you're not familiar with C++, but this sort of encapsulates the same function that we just had before. It just does it inside of a class. So we can use it just like a function. It's basically a function pointer. We can treat it like that. But there's some technical reasons why we have to do this with CUDA today. And also there's more things that you can do with functors than you could with just function pointers. So we'll see some concrete examples of where this is more useful to us. But just to illustrate a simple example where we can add numbers together like before. Okay, and the last background slide, here I have a simple algorithm that just takes in 2 vectors described by pointers. So x and y are 2 input vectors. It'll apply some function, some binary function to them, and store the value in a third array. So the things in Thrust are semantically similar to this. They just get carried out in CUDA. The interface is a little bit different, but this is sort of a very simple example of a templated algorithm that performs a vector-vector operation. You could imagine doing a generalized reduction using the same kind of approach where you might fill in add or maximum or something like that to describe different reductions. Okay, so Thrust has a lot of different algorithms. I've only shown a few, but it has lots of transformations. So applying a function to a vector, so your kind of map operations. It does reductions, prefix sums, stream compaction, sorting. It does sorting based on, say, keys and values also, which is a useful feature. And you can do this for lots of different types. So in the examples I've shown so far, I've just looked at integers or floats, which are probably your most common examples. But you also, there's reason to do user-defined structures. So maybe 2D vectors or 3D vectors, or more specialized types. And you can plug in your own operators. So in the examples I've shown, I might have used a plus or maximum on integers, but really you can do anything. If you have 2 structures that describe records for some database that you're using, you can define sorting by just defining a comparison function to compare those 2 objects. So if you implement the less than operation between those 2, then you can sort with Thrust. Okay, so as I mentioned before, you can do, the algorithms support general types and operators, and this just shows you the way that you specify that for the reduce function. So in either case, we're working on the device, but we have in one case a sequence of integers, in the other case a sequence of floating point numbers. And if you just want to take the sum of them, you can just call reduce, and it implicitly sort of fills in these additional optional parameters with some defaults. So the default reduction is to take the sum of the numbers and initialize the sum to 0. You could also take, say, the maximum, initializing the value to 0 as well, or some kind of user-defined operation. So we'll see some more compelling examples of this later, but I just want to introduce the basic algorithms that are available to you. Okay, so here's an example of a user-defined operation. We have now, instead of float or int, we have a float 2. So we have a structure with 2 floats inside. And we want to just take a sequence of them and negate them. So we want to take the x component and negate that, and take the y component and negate that as well. And this is how you would describe that in Thrust. You would have your sequences here, your device vectors. You'd write this functor, which just has a member that negates the floats. So it takes as argument a float 2 and returns one that's been negated. And then you use the transform function, giving it the input sequence, the beginning of the output sequence, and the function that you want to apply. There's another version of the transform function that takes in 2 input sequences and writes the result to a single output. But here we're using the one-to-one transformation. Okay, and here's an example of a user-defined sorting operation. Again, we're using the float2 structures. This is the standard built-in float2 in CUDA. And we define our own way of comparing these two. You could define other ways of comparing them using both, say, the x and y components of the vector. But in this case, we're just going to sort on the x component. This is the kind of thing you might do if you have to build a data structure using some user-defined type to bring the similar ones together. Okay. The function objects I've shown so far are pretty simple. They just have a single member function that gets invoked. You can also use some variables inside them to do more interesting things. In this case, I have a device vector full of integers, and I just want to count how many of them are greater than some threshold. So I pick the number 10. I pass that into the function object. That gets saved as in the variable threshold. And then when that functor gets called on the members of this vector, it's going to compare that value to the threshold and return true or false. So using this single line of code down here, I can count all the values that are greater than a particular threshold. You could define your own to compute, say, the even or odd elements and how many there are, or other qualities. Just a matter of convention, when you have a function object that returns a Boolean, it's called a predicate. It's really no different. It's just a special case, but that's the terminology that's used. Okay, so to summarize what we've looked at in this section, we have generic algorithms. You can provide your own either types or operators, and either of those options is useful. An important thing to, I guess, note is that even though we have a lot of mechanics going on under the hood, you provide a small amount of information, and Thrust infers all of this using some C++ template magic. Most of it happens at compile time, so there's really not much overhead associated with this kind of flexibility. At the end of the day, you get a very highly optimized implementation of that, and you get it for free. Okay, this is the second to last section I have. We'll talk about fancy iterators. So the iterators I described before, we thought of just as pointers. They have pointers and they have some metadata associated with them to determine whether they're on the host or the device. These fancy iterators are going to be like iterators, except they're going to do something slightly different. They may not actually correspond to memory, or they may provide or perform some operation before they produce a value for us. And we have 5 of these so far in Thrust, and I'll describe why these things are useful. Okay, so the simplest fancy iterator we have is this constant iterator. So sometimes when you have an algorithm, you want to feed it input that is just a sequence of constant values. If you have, say, a function and you want to specialize it for a particular case, maybe you have a function that adds 2 vectors together and stores the result in a third, and you want to use that to just increment all the values in that first array by 1. One approach is that you could fill an array explicitly with the value 1 and then use that generic algorithm to perform the increment. Another approach is to have an iterator like this constant iterator that returns that value, that constant value, each time it's dereferenced, but doesn't actually live anywhere in memory. So you get the effect. It's sort of a virtual array sitting in memory that has the same value, but it doesn't live explicitly in memory. And therefore, it doesn't cost us anything, either in terms of memory capacity or memory bandwidth. We can dereference this thing using just a few instructions. So here's an example where I initialize a constant iterator with the value 10, and then whenever I access it, it returns 10. No matter if I start at the beginning or access the 100th element, it'll give me the result 10. And then you can pass these into algorithms just like you could with normal iterators. So if I have a sequence of 3 elements and they happen to be these constant iterators, I'll get 10, 10, 10, and the sum of 30 in this case. A slightly more interesting iterator is this counting iterator. It's very similar to the one I just introduced, very similar to the constant iterator, except this one increments each time. So whatever you initialize it to will be the first value in that sequence, and then if you access it, it just increments sequentially. So this is, again, useful if you have a generic algorithm that takes, say, 2 sequences, and in the second sequence you just want this kind of incremental sequence. If you're familiar with things like Python, this is basically what you would get if you did enumerate on your existing sequence. So this alone is not very useful, but when you pass it into an algorithm that takes multiple sequences, it can be very useful for you. Transform iterator. So normally in memory we have just some, so this would be an array in memory with the explicit values x, y, and z. And sometimes we want to apply a function to that and feed that f of x and f of y and f of z into the algorithm. So you could imagine, suppose, and I have an example later, I guess. Sometimes you want to perform an algorithm on a sequence, but you want to perform some transformation before you perform that algorithm. So a good example is a reduction. You don't always want to reduce x, y, and z. Sometimes you want to reduce the absolute value of x, y, and z, or the square of x, y, and z. And it would be very wasteful to, in one operation, compute those values and store them in memory and then read them back. It's much more efficient to apply the transformation as you read them from memory in one step. Okay, so here's an example of that. I have an array in memory with the values 10, 20, and 30. I'm going to negate those. I'm going to apply a negation transformation to those. And whenever I read these values, I get the negated results. So again, we can use reduce on these. This is not a good example because you could just factor out the minus. But we'll see a more interesting example of this later on. Okay, so the last iterator I'll talk about today is the zip iterator. And this is probably the most useful one, although it's a bit weird to work with. It allows us to take multiple sequences. So in this case, I have 2 sequences, A, B, C, and X, Y, Z, and zip them together. And that means I take 2 or more sequences, and I generate a sequence of tuples. So if I had 3 sequences, I would have tuples with 3 elements, or 4 sequences, tuples with 4 elements. And the reason to do this is that the algorithms we provide usually only operate on 1 or 2 sequences. So if you want to do a reduction, you can only operate on a single sequence. So if you want to process multiple sequences together, say you want to reduce pairs together, you want to pull in 2 sequences and perform a reduction on those, you'll need to use zip iterator to do that kind of operation. So on the one hand, it's a way of feeding in several sequences at once to these algorithms. And there's also a performance reason to do that due to the memory coalescing requirements of the device. We'll get a concrete example of that later on. But if you're familiar with the memory coalescing restrictions, it should be apparent that if you were to store these in memory as tuples or structures, then when you were to access them, they would not be accessed in a coalesced way. It would give you pretty poor memory performance. So in this example, I have a sequence of integers, a sequence of characters, and I create a zip iterator. So this is what I mean when I say it's a bit cumbersome to work with. You build these pretty large expressions just to define the iterators you're working with. But the value is still good. It's a nice way of describing a lot of algorithms that would be even more difficult to write on your own. So when we access the zip iterator, we'll get things like tuple. So in this case, we're getting a tuple with 2 elements. And we can do things, like I said, a reduction of these. So we can zip these 2 sequences together, treat them as a sequence of tuples, and then compute the maximum. Other examples, you might use this to figure out the, before we showed how to use reduce to compute the maximum element of an array. Using this kind of approach, you can figure out what the index of the maximum element in that array is. So you can pass in a pair of sequences and then use those tuples, operate on those tuples to figure out what you need. Okay, so in the last section, I'll talk about 3 different sort of high-level optimizations, things you should be thinking about when using a high-level library like Thrust. The first is Fusion, and Fusion just says there are lots of different ways that you can exploit Fusion, but the simplest is just to combine several different operations together. Like if you want to compute the sum of a sequence of values and apply f to those, then you should fuse that transformation with the reduction and just read those values once from memory. The second strategy is this structure of arrays. So rather than storing, if you have a structure, rather than storing those structs, back to back to back in an array, it is usually better to store them as separate arrays of one type. So if you want to store an array of float 3s, or logically float 3s, instead of storing float 3 as a bunch of structures, it's better to have 3 separate arrays, one for the x component, one for the y component, and one for the z component. And that's the structure of arrays layout. And the last, I'll show some examples. What's that?
Is that really true for float 3s then?
Yes. Float 2s and float 4s can be faster because they obey the coalescing rules. But float 3s do not obey the coalescing rules. So if you just read in, like copy an array of float 3s from one place to another, it'll actually be 1/3 the performance you would get from a float 2 or a float 4. Does that make sense? I'll show that exact example here.
Float 3s magically in some multiplicity that lined up on an even power of 2.
Well, you can't.
Obey the coalescing rules or no?
I mean, 3 is relatively prime to 2, so there's no, it will never obey that. So, yeah, the coalescing rules are very strict. You can only read, 32-bit words, 64-bit words, and 128-bit words, and they must live on the right boundaries. So it's both the boundary and the size of the structure you're working with. So it's very specific in what you can do. And if you don't believe me, I have the performance numbers to back it up. It's okay. Okay, so with Fusion. So a simple example of Fusion is if we want to compute, say, the norm of a vector. So the mathematical norm here is just you take the sum of squares and then you take the square root of that. And if you do this naively, if you do this in 2 separate operations, as I've illustrated here, it's not terrible. The GPU is very fast, has a lot of memory bandwidth, so you may not even notice. But it's quite bad. And the reason for that is that first we have to create this temporary array. So we're taking in this x vector and computing its norm. We have to create a temporary array. Then we have to read in x, compute the squares, and write those back out to temp. And then in a final operation, we'll sum those temporary values together and compute the square root. So we read in the values, compute the squares, write those back out, and then we read in the squares again. So it's basically 3 memory transactions for each element of this x vector. A better way to do this is using the fused approach. And in the fused approach, we have this built-in function called transform reduce. In other cases, you'll have to use the transform iterator to do the fused operation. But transform reduce is just like reduce, except it allows us to specify a transformation to apply to the element before doing the reduction. So in this case, we're going to square the elements before we add them together. And this is actually quite fast. This is about as fast as it gets on CUDA. And we've described it without having to write a special CUDA kernel or algorithm for this kind of implementation. So this is a very simple example of fusion. You can come up with other ones. For instance, somebody on our mailing list showed how to compute all the sort of statistical norms up through like the fourth moment or something using a single reduction. So you can get pretty sophisticated with this. But most opportunities are like this. You have a very straightforward combination, like a transformation or reduction, that you can fuse together. Okay. So with the array of structures, as I mentioned, so the array of structures approach, this is generally the bad idea, or the slower approach, is to just say device vector of float 3. Or you could do device vector of mystruct, where mystruct has several different components in it. The structure of arrays format is to have, you have the same, a different representation of the same kind of data. So you have 3 separate floating point vectors. It's kind of annoying because you all of a sudden have to manage several of these. If your structure had 8 elements, this is a bit cumbersome to work with. But the performance advantage is pretty significant, so it generally pays off in the end. In the example I'll show the code for, it turns out to be 2.8x faster. Okay, so this is the structure of arrays format, or implementation. We have an array of float 3s, and we're going to transform them. And the way we transform them will just be to rotate them. And this just defines a 3x3 matrix. So there's nothing particular about this case. It doesn't really matter whether you're doing a rotation or just a copy. The performance implications here, and the reason that this is undesirable, is that when we read these float 3s from memory, it'll actually correspond to 3 different transactions. So the memory bandwidth will be about 1/3 what we might expect if we were just reading floating point numbers. So anyway, this is just as I explained earlier, because the coalescing rules are very specific. If this was a float 2 instead of a float 3, this would be okay, or a float 4 actually would also be okay. But the particular case of float 3, or most structures that you might write yourself, if they have any sort of irregularity to them, would get you poor performance like this example. The faster approach is using this zip iterator with 3 separate arrays. So here we have 3 different device vectors, and we read them we zip them together using the zip iterator. So the way to think of this is it pulls these elements together on the fly into a tuple. And the tuple just exists in the registers of the chip. It doesn't actually exist anywhere in memory. It just comes together programmatically. And we can really write the same kind of code with this. We have a few changes. So instead of float 3 down here, we just have float with 3 different arrays. And up here in the arguments to the functor, we have a tuple rather than a float 3. But that's basically it. We can treat it just like it was a structure and work with it internally however we'd like. So it's a fairly simple transformation from one to the next. And the performance benefit is pretty substantial. So it's definitely a worthwhile optimization. Okay, so in the last one, I'll show an example of where counting iterator is useful. The example will be to compute the index of the element with the smallest value. So this is the Aardman, if you're familiar with that kind of terminology. And the savings we'll get is we won't have to store these values in memory, and we won't have to actually read them either. So this is the approach that you might use without the constant, or the counting iterator. You'll have a vector of floats in this case, and we want to find the index of the smallest value. And we would build this, we might build this array of indices, starting with 0 and just incrementing from there. And this is maybe a little too complicated to do in real time, but the basic approach is that we have an array of values, an array of integers. We zip them into tuples, and then look at the tuples to decide, to keep track of what the indices of those elements are. So we'll pull the first element of the values array alongside the index 0, and build a tuple out of that, and then reduce all the tuples together. So the way the reduction works is pretty simple. We just compare the two tuples together, and if the left tuple is smaller, we'll return that. If the right tuple, otherwise we'll return the right tuple. And at the end of the day, we'll get a result, smallest, I've named it here, where the first element of the tuple is the smallest value, and the second element of the tuple is the index of that value. So if you're familiar with, say, Python, then this is something you might write with a numerator or something like that. If not, it may take some time to review. But this is just to illustrate the slower implementation where we have these explicit indices in memory. The alternative is to use counting iterator, and it basically looks the same, but instead of a device vector full of integers, we just have used the counting iterator. So we zip these up, the values along with the counting iterator, and use pretty much the same algorithm above. So we're doing a reduction, but this time the second element of the tuple is just being computed on the fly rather than being read from memory. Okay, just to summarize the speedups we get using these best practices, about factor of 3 across the board here. So these are definitely worthwhile. Whether you use these, through Thrust or on your own in CUDA-C, these are all good things to keep in mind. They're just things that are pretty easy to express using Thrust. Okay, so that concludes my talk. There's some resources here. I guess this isn't too useful to you on a slide, but I guess, Jared, you can mail them these links if you haven't looked at them already. So anyway, thank you for your attention, and I'll take your questions now. Okay.
Can you just kind of review some of the coalescing rules, or maybe should we do this after class? I don't know.
We can do that now. The easiest way to describe it is that if you have a built-in type, an array of a built-in type, like a float or integer, those will coalesce. So if you read those, a contiguous block of those, they will coalesce. And that will be, the way to describe it is that when it physically goes out to get that memory, it'll do so in a single operation. If you access something with, say, a non-unit stride.
And that's a contiguous read, right?
Yes, so there's, on GT200, it's a little bit more flexible, so it could be offset by an amount, and that would be less efficient, but it still does it.
That's a strided read, not like a map.
That's right. So there's two things. There's the coalescibility of the type, so it has to be a 32-bit or a 64-bit or 128-bit value that you're reading. And it's also beneficial if it starts at the appropriate boundary. So if it's aligned properly, that's also a consideration. If it's not aligned but it does coalesce, it's maybe like a 30% reduction. If it's not coalesced, then it could be as bad as 90% reduction. So if you read every 16th value in memory, you're going to get 1/10 the performance you'd get if you read every value and it was aligned properly. The reason to talk about structure of arrays is that as long as the independent arrays, in this case we did 3 floating point arrays, but they could be integers and doubles and stuff. The reason to do that is that you get coalescing kind of for free. You don't have to think too hard about whether you're going to get it or not. As long as the type in that array coalesces, you're good to go. The difficulty with doing your own sort of user-defined structs is that not only do you have to have the right size, like if you were to define your own float2, it actually won't coalesce in CUDA because it has to have these appropriate sort of tags on it as well, and that's pretty difficult to do. So if you use float2s or float4s or the other vector types that CUDA provides, with the exception of the float3s and stuff, those will coalesce. If you do your own, they won't coalesce, so you'll probably want to do structure of arrays layout.
For more, please visit us at stanford.edu.